So the extended information filter is a variant of the Kalman filter, again, but compared to the UKF, it doesn't really address the linearization as the issue. It just performs the computations in a different space. So if we, again, revisit the Gaussian distribution, the typical Gaussian distribution is described by its two moments, the mean and the covariance matrix. So if you look to the equation for the Gaussian, which is this one, the parameters in there, the free parameters, is the mean and is the covariance matrix. And he described that based on the mean and the covariance. And this is what is called the moment form or the standard form of the Gaussian distribution. That's something that you probably all know. What you may not know is that there's an alternative way to describe that, which is typically called canonical form or canonical parameterization or information form, two expressions you find. And this is just an alternative way of describing a Gaussian distribution. It again uses a matrix. It again uses a vector, but it's not the mean and it's not the covariance matrix. Instead, it uses the so-called information matrix, which is the inverse of the covariance matrix. So the information matrix is typically called omega, and it's just exactly omega, and you have an information vector xi, again a matrix and an information vector. I was a little bit too fast. And the information matrix is given by the inverse of the covariance matrix, and the information vector is given by the information matrix times the mean. And based on this parameterization, it's just an alternative parameterization, I can also represent a Gaussian distribution and can describe exactly the same probability distribution, except that I don't have a mean that I use and I don't have a covariance matrix that I use. I have an information matrix and an information vector that I use. But I can use this in a very, very similar way, or exactly in the same way. However, if you operate in information spaces, some of the things that are difficult in the normal form become easy, but some things which have been easy before become more difficult. So you may say, I don't win anything, because if one thing was easy, one thing was hard, I refer here to marginalization and conditioning, it's exactly the other way around in the other space. But it can be an advantage depending on which operation you execute more often, or if you have certain properties that you want to exploit, it may make sense to move to the information space and not operate in the regular space. The important thing to note is that you can perfectly convert between the information space and between the moment space. So if you want to compute your moments, so your covariance matrix and your mean, you just need to invert the information matrix and multiply the inverted information matrix, so the covariance matrix, times the information vector. And the other way around, if you want to compute omega, the information matrix, you just need to invert the covariance matrix. And if you want to compute the information vector, you just need to multiply the information matrix times the mean. So you can convert forth and back between both representations. What's the cost of converting those between those representations? So if I have moment form, I want to obtain information form and the other way around. What's the computational cost of doing that?
So we have to invert the matrix, so it's n to the power of 2.4.
Exactly. So the important operation is that we have to invert a matrix, which is cubic in n to the power of 3 if you use in the most trivial inverting algorithm. If you use improved inverting algorithms, you are, as you said correctly, n to the power of 2.4. But again, it's still in the class of cubic complexity. So that's important. Converting between those representations is something which is very costly. So that's nothing we typically want to do. We can do it, but it's a costly operation. Okay, so the first thing I would like to do is derive how the Gaussian information form looks like. Actually, tell you that it is exactly the same. Therefore, we start with the Gaussian distribution. So this is the definition of the Gaussian distribution over here. And we now want to change the expression over here so that we end up with our distribution in information form. So the first thing we do is we take our expression here and expand all these multiplications which are involved in here. So we end up in exactly this expression. So whatever is underlined in red in the previous line is this expression which lead to the change. So what we're doing here is we have 0.5 x times the information matrix times x, so this is exactly this term over here, and so on and so forth. So it's just standard multiplications and whatever one transformation you transposition that you need to do in order to combine x sigma to the power of minus 1 mu and the mu on the other side. But that's easily doing. So we end up with exactly this term over here. The next thing we do is we kind of split this function over here. So when I have 2 times the exponential of this term up till here and times x of this guy over here. That's something we can also do. So we end up with exactly this term. So this guy corresponds to this term over here, and this guy corresponds to this term over here. So what is special about this term over here? If you look to this term, or this one over here, is there something which is notable? So on which quantities does this term depend on? Yes?
It's independent of our x and
exactly.
depends on the mean and the covariance.
So it's independent of the x, so independent of our variable. So it's basically a constant. So what we do is we combine this constant over here and with this term over here because it's just a constant. So we can rewrite that and put this line over here just into my constant because it's just a constant. I don't care about it. And so the thing which remains is the second line, is the second part over here. Okay? So now let's have a closer look to the individual elements in here. So this guy over here, sigma to the power of minus 1, the inverse of the covariance matrix was what? Was the information matrix. So we can replace this guy over here by omega. And this term over here, which is, again, the information matrix, times the mean, which was exactly the information vector. So I can replace this term by the information vector. If I do that, except they end up in this form over here, so this expression leads to this expression leads to this expression, and that's it. This is my parameterization in the canonical form or in information form. So I have my x, which is multiplied here. This is actually a quadratic form, something notable, plus the transposed vector x multiplied by the information vector. So what we end up having is a dual representation. So this is what the information or canonical parameterization looks like. Again, this was kind of our constant. This is the constant which came from the Gaussian. And so now, exactly, we have our form here, and this is our canonical representation. On the bottom, we have the moment representation as you all know it. So it's a dual representation, and we just did the derivation, and it's expresses exactly the same distribution. So there's no change in the distribution itself. What is, however, notable, and as I said before, that some things which are easy in the moment parameterization get more tricky in information form and exactly the other way around. And this becomes clear if you look to the marginalization and conditioning of these distributions. So what you see here is kind of the covariance form or the information form, so kind of the standard form and canonical parameterization. We looked into this already before, I think in the second or third lecture. So if I want to marginalize out a variable in covariance form, in the standard form, that's really easy. I just need to cut out a part of the covariance matrix and a part of my vector. It's just kind of cutting this out, taking this out. It's trivially done. However, for the conditioning, the problem is I need to take out a part of the matrix, actually of the covariance matrix, the part which It's a covariance matrix on B, and invert that. And this inversion is a costly operation. So conditioning is expensive in the standard form, but marginalization is easy. And for the information form, it's exactly the other way around. The reason why this is the case is that I already have this matrix, this inverted block, in my information form available, because I already operate in the inverted space. So in this case, the marginalization is costly, because I have here to invert the information matrix, but therefore the conditioning is really easy. So, and now this shows that depending on what you want to do, one or the other representation may be advantageous. Okay, so again, these two things are trivial, and these two things are computationally expensive. I mean, still, it's not difficult to do that, but it's computationally very costly, because you may need to invert potentially very large matrices. Okay, we can now use this, similar as we did it for the unscented Kalman filter, to revisit the Kalman filter algorithm and say, how do we need to change the Kalman filter algorithm to operate in information form? Again, these are just two different parameterizations for a Gaussian. So they have the same expressiveness, but one thing is more expensive in one form and one thing is more expressive in the other form. And so we take the standard Kalman filter that we introduced in chapter 4, and now want to bring this Kalman filter into an information filter. So move from Kalman filtering to information filtering. That means doing all the computations, not using the mean and the covariance matrix, but the information vector and the information matrix. Okay, so again, we start with the first part over here. And again, the first part at least I would like to do on the blackboard together with you. So let's start with line 3. That's what we have. So we had, okay, let's write down AT, the previous belief, A transposed T plus RT. Now let's move to information form. If you want to do everything in information form, how do we end up with information form? So this is this guy, to the power of -1, according to the definition. So what is it? Yeah.
We turn around the AT, so we have the AT transpose.
It's actually easier than that. Just copy the equation down here. T minus 1, AT transpose plus RT to the power of -1. Otherwise, we have this sum in here. So what you wanted to do would only work if it would be just a product of matrices. You can't do that with a sum of matrices. And this guy doesn't exist in information form. What do I have to replace it with? Yeah. So this turns into A transposed omega. This is actually not bar. Okay, without bar. T minus 1, but inverted. A transposed plus RT to the power of -1. That's it. So, and that's exactly what we have there. So we can compute the the predicted information matrix after the prediction step exactly by these operations here. Again, that's costly. We need to invert our information matrix to do that, and we need to invert the resulting expression here. So it's a costly operation. You want the same thing, do the same thing for the information vector as well? Okay. So we have xi, which is the information vector, which was given what was the definition of the information vector? Okay, if you forgot it, let's go back. Okay, we have to move back for. So the information vector was the covariance matrix inverted times the mean. So we can already write that as information matrix times the mean. Minus 1, of course. So previous time step. Okay, burp. So this is fine. So we can keep our information matrix from the previous time step. What was the mean? How was the mean computed in the Kalman filter? Was the matrix A and matrix B involved? Was a linear function? Random guessing. Yeah, A times minus 1. Yeah. Plus B times U T. Exactly. So this was the expression to turn the previous belief into the previous mean into the predicted mean. We don't have the mean in here, so we have to do another step. Sigma t minus 1 a, and the mean was defined as the inverse information matrix times the information vector. So we have to replace this guy because we don't have the mean, we only have it in information form. So this is t minus 1 to the power of minus 1 times psi t minus 1. So the information vector of the previous point in time plus bt ut. Okay, skip the time index here. but. That's it. We're able to do that. Again, we need to invert our information matrix. It's again a costly operation. So how does this change? Okay, we can actually just write down the first two lines of the information filter algorithm. How does this compare to the Kalman filter? What we have done here. What was the computational complexity of the prediction step of the Kalman filter? It was linear in the SLAM case because there the prediction step only affected a constant subset of the variables. In general, it involves these matrix multiplications on the large scale, and so if the kind of the transition affects all the elements, then this will lead to a quadratic cost. It was only linear for the for EKF SLAM because there we had the fact that the robot motion only affects the first 3 dimensions and not the others. And then we just needed to compute the correlation between those 3 variables and all the landmarks, which gave us linear complexity. So in SLAM it is linear, but in general it's quadratic. But again, here, this is not quadratic, that's cubic. So what we learned from this algorithm, or from the first 2 lines of the information filter algorithm, is that the prediction step becomes more costly in information form. Okay, let's look to the correction step. correction step is derived in a slightly different way, and because that's the easier way of doing that. And we can just say, okay, the prediction step was corresponding to the prediction step in the base filter, because we're using the base filter framework here, and that the final belief at time t was computed by multiplying the observation model with the predicted belief. The predicted belief we computed already on the previous slide, so we can actually use this directly and express it. So we have a normalization constant times, this was the Gaussian of the observation model, if you remember correctly. So this C times X was exactly the mapping from the current state to the information space. So this was the predicted observation, the difference between the obtained observation and the predicted observation. So this guy here corresponds to this line over here, and that is our predicted belief. Okay. So what we can do is we combine those two terms. That is our equation. The next thing we can just do the multiplication, getting rid of all the brackets, similar to before. So we get this very, very long expression. And now we can simply sort them according to elements which involve computing, so again, constant terms as we did it before. So the constant terms kind of disappear now. So those which only like the term, the mean information matrix mean, this term is again hidden. Therefore, we have a new constant here. This is twice primed. And then we can actually group those elements, those which depend only on x, and those which are quadratic form in x. So if x times matrix times x. So we can actually group them together and obtain a form which is minus half x transpose times a matrix times x and plus x times a vector. And if we now look to the definition of the information form, we can say, that's easy. So this must be the information matrix, this block over here, and this must be the information vector. So it's kind of the very, very, very simple way of deriving that. We said, okay, we start with what we know from the Gaussian world. We just rearrange the individual terms, group those terms. So we say there's something where x multiplied with the matrix times x, and some other term where it's x times a vector. And given the analogy we know from the information form, how the information form is built up, we can directly see, okay, this must then be the information matrix, and this must be the information vector. So from this line here, we can then derive that the information matrix is computed as C transpose, so this was a mapping which maps, C was a mapping which maps from the states to the observations, times the inverse of the uncertainty of our sensor, times C plus our predicted belief, and here again, the term only that we have, here the information vector and here our observation. So what you see in here, the only matrix that we have to invert in this term, in this equation over here, is actually this Q. And Q is just the dimensionality of our observations. So if we think about large-scale estimation problems like SLAM, that's a constant, because this is a constant size. So the only thing we need to do in here is we have some matrix multiplications we need to carry out. So that's a step which we can do very, very efficiently. So we can put those two lines down here. So there's the prediction step and the correction step. There's no explicit computation of the Kalman gain in here, but again we have this weighing of our predicted belief combined with the uncertainty of the observation. So we come up with this very compact formula. And we can now see in here there's no large matrix that I need to invert down here. That means the computational cost of the correction step is no lower compared to the Kalman filter. So if we we have the prediction step and the correction step. And the differences, okay, we discussed this basically before on the slides, is that the Kalman filter was cheap in the prediction and expensive in the correction step. And now for the information filter, exactly the other way around. It's expensive in the prediction step, but efficient in the correction step. And depending on how often I need to do one step or what properties I have of those matrices, one can exploit the one or the other formulation to be more efficient. The other thing which is the case is, as you said before, or as was said correctly, inverting a matrix is expensive. Inverting a matrix is only expensive if this matrix is dense. If this matrix is very sparse, it means the majority of elements are 0. You can do more efficient techniques for inverting matrices. It's actually linear in the number, roughly linear in the number of non-zero elements if it is a very sparse matrix. And just something we will see actually in the next week is that depending on which form I'm operating on, some matrices are sparse or nearly sparse, or I can make them sparse without changing the matrix too much. And this is something I can additionally exploit, that then even inverting a matrix can be comparably cheap. This is just properties that we will see which hold for the SLAM problem on how the information matrix behaves and how the covariance matrix behave. And we can actually show that the covariance matrix gets dense, the information matrix is approximatively sparse, or can be. So they are very tiny elements, we can approximate them by 0, and then be more efficient in doing some things. And this then leads to the sparse extended information filter, which we will discuss next week, or maybe we need 2 weeks for that because it's a little bit more involved. But that's kind of one way for exploiting this information space and saying, I have a certain application and certain operations for my applications are costly or cheap, and then I choose the form, in this case the information form, which better supports that. Okay, so this again, the complexities written down in a more formal way. Again, this is the star over here which says this can be done potentially faster depending on the application, especially for the application we are looking here in this course, which was SLAM or EKF SLAM. Then this step is linear and not quadratic in the number of elements. But the reason was again only that the update only affected a small number of the states. Okay. Extended information filter. That's clearly the next step. So we had our information filter as we had the Kalman filter. Again, we have the problem of nonlinear functions. So what we actually need to do is go a step further and do the extended information filter. Okay, so extended information filter is the kind of dual representation of the extended Kalman filter. And so what changed from going from the Kalman filter to the extended Kalman filter was that we are allowing our nonlinear function g and our nonlinear function h to make the mapping for the prediction step and for the correction step, and we linearized them. And this is exactly what the extended information filter does as well. So we have our function g, which we approximated by using our linearization point, the previous mean, and our Jacobian, and then see how far we are away from the Jacobian. So this is a linear function. And the same for the observation function. We approximated this nonlinear function by evaluating this function at the linearization point, which is the predicted belief at time t, and then have the Jacobian here. So that's the Jacobian g and the Jacobian h, and this way we have linear functions. So we just look which steps of the Kalman filter changed, going from the Kalman filter to the extended Kalman filter, and see where we need to make those changes for the extended information filter as well. So we have seen that the Jacobian G replaced this matrix A. So if you look down here to the EIF extended information filter, it's exactly, we just need to replace the A by the matrix G. So that was easy. It gets a little bit more involved for the nonlinear function. The problem is that the nonlinear function requires the linearization point, which was the previous mean. And it can't deal with an information vector as an input, unless we can smartly rewrite our function, but that should be pretty impossible. So we need as input the previous mean in order to make the prediction step with our nonlinear function. As a result of that, we need, if we do this in information space, we first need to recompute the mean by inverting our information matrix times the information vector in order to obtain the mean estimate, propagate it through this nonlinear function g, and then multiply it with the information matrix. So if we can replace this, so from the extended Kalman filter to the extended information filter, we first need to recover the mean, then map the mean to the predicted mean, and then convert it back to information spaces. And that's a problem in here already, because we need to again invert our information matrix. So some of the gain that we had before, we lost now in this extended information filter. Because given if we would have a way to propagate the information vector more efficiently, we could do that. But if we, let's say, do the standard transition from the extended Kalman filter to the extended information filter, we have the problem that we have to have the inverted information matrix available here. And if this inversion is expensive, that's critical. As I said before, as we will see next week, there are ways, or there are certain situations where we can approximate it by a matrix which we can invert faster. But if this is not the case, this step also gets very expensive. And the correction step for the extended information filter, we can derive exactly in the same way as we did this for the information filter. So we take our final belief is the observation model times the predicted belief. We can do exactly the same operation that we did before. We group those elements, throw away everything which is constant, or move it outside, and then come up with an information matrix and an information vector. So we don't have here, so this term here replaced this ct times xt, which is now the linearized function, and the same in here. And we need to multiply, this is multiplied already, so this is the prediction, the observation model and the previous belief. And then we could do exactly the same operation that we just did before, grouping those elements. And then we end up that this is our information matrix and our information vector that we need to have. And again, here we have the problem. In order to execute, to get this, to make this transformation through the nonlinear function, we again need to have the predicted mean. So that mean that we computed before, we still need that. And therefore, the extended information filter has the problem that both steps actually need the mean estimate. We need to make sure we have that mean estimate. And this is then finally the extended information filter, which is kind of a dual representation for the extended Kalman filter that operates in information space. The only thing we need to do, we have to kind of move back to the moment form in order to use our nonlinear functions, because our nonlinear functions are defined in the moment space, in the space of moments, and not in information space. That's kind of one thing where why this doesn't look as clean as the basic information filter was looking before, because we have to make this step forth and back between those forms. So if we just compare the extended information filter and the extended Kalman filter, again, the complexities between the prediction and the correction step, I say differ here. They can differ if I can recover the mean in an efficient way. Otherwise, I turn into problems that both steps actually become expensive. It has, however, the same expressiveness. So if you can do these operations and you don't care about your timing, the information filter gives you the same result. Then the extended information filter gives you the same result than the extended Kalman filter. It's reported to be in some situations numerically more stable, although other people doubt that. So there are some people claiming it's better, but the difference is really, really small. And therefore, most people stick with the EKF form because we simply don't have to convert back between those spaces. So in standard extended information filter is typically not used, at least for solving SLAM or mapping problems. But there are extensions of the extended information filter, and there's a sparse extended information filter I will talk about next week. That's the reason why I introduced the filter here, which makes some approximations to some of the steps in here, and this way is able to derive a very efficient algorithm that we can actually use to address the SLAM problem. Okay, so to summarize, what you have seen in this second lecture here is that Gaussian can not only be represented in the moment form, they can also use canonical representation or the information form to represent the same distribution. And we can use this then to do information filtering. So it means filtering in information form, or filtering in information form. We can derive from the Kalman filter the information filter, and from the extended Kalman filter the extended information filter. And so if we compare those, one of the steps can be more efficient than the other step, but in sum they have the same complexity, because if I need to do both steps with the same amount of times. So the application really tells us which system is more suitable for us, or which one is easier to maintain. Does it make sense to change into information form? That really depends on the application. And again, if you want to read more about that, Probabilistic Robotics book 3.5 has an in-depth introduction into the extended information filter, and then which is kind of the basic knowledge that we will need next week for going into the sparse extended information filter. So whenever you're today saying, oh, this information filtering was not completely clear to me, revisit the slides, or maybe read this article, or if you have a question, ask me, or Fabrizio, or Rainer, whoever is here to help you. Because it should be kind of information filtering should be pretty clear to you, because next week sparse extended information filtering will get a little bit more mathematical, a little bit more tricky in some of those details. So it is worth to make sure that you know what an extended information filter is and how it works. That's it from my side for today. I'm looking forward to see you next week, and have a nice week. Bye-bye.